right, this is our week 6, day 2 video, and we're switching gears. So now we're going to be talking about probability. So we've done all of our conversion things that we needed to do, and now we're moving on to our next topic. How do we calculate probability? So there's a few things we need to go over before we can do that. So 6b1 is over the probability of equally likely outcomes. And there's a few fundamental rules of probability. Number one, the probability of any event A, which we consider P of A, that's how we write it with that parentheses around the event, must be greater than or equal to 0. So you can't have a negative chance, like it can't be negative 10% chance. So it has to be 0 or bigger, but it has to be less than or equal to 1, which we consider, remember, 100% if we change that to percent form. So you can't have more than 100% chance of something happening. So our probability will be a decimal point between 0 and 1. And if we think about that in percent form, probability happens between 0% to 100% chance. So either impossible, which would be 0%, or certain, which is 100%. Most of the time, probability is going to be somewhere in between that, some other percentage. Now, if you have a set of outcomes in an experiment, so for example, rolling a die, there's 6 sides on a die. So the probability of each individual side happening, so probability of a 1 or a 2 or a 3 or a 4 or a 5 or a 6, those are all unique outcomes in those experiments. Getting a different number when you roll, that's a unique outcome. The sum of all those individual probabilities should equal the entire probability set, which is 100%. So if your sample space is, like I said, rolling a die, so getting a 1, 2, 3, 4, 5, or 6, then the probability of each of those individual things occurring should add up to 100% or 1 if we're in decimal form. Now, when you actually do something, you expect a certain thing to happen sometimes. So like if I flip a coin, most people will say, I expect heads 50% of the time and tails 50% of the time. Even if you didn't know what you were doing, you were actually calculating that probability. You're saying there's 2 sides to a coin and a head is one of them. So I think I have a 1 in 2 chance of flipping a heads. Now, if you just do that 10 times in a row, you may not get 50% heads and 50% tails. This is what this next statement is about. It says the law of large numbers says that if a probability experiment is repeated many times, so the big numbers is the key there, the probability of a certain event observed will get closer to what we consider the theoretical probability. So theoretical is what I expected. I expect 50% heads and 50% tails because I know there's only 2 sides to that coin. If the experiment has equally likely outcomes, we can calculate the probability using the theoretical model for equally likely outcomes. So that's, like I said, the 1/2 heads, 1/2 tails. But to truly see that in action, if you're going to do an experiment, you need to repeat the experiment many, many times, okay? Theoretical method for equally likely outcomes. So count the total number of possible outcomes. Let A be the event that you're looking for. Then among the possible outcomes, how many ways did event A occur? The probability P of A is the number of ways that you got what you wanted, which is outcome A, divided by all possible outcomes. So that's what this is written here. So if I'm looking for probability of heads, there's only 1 head on a coin. That's why there'd be a 1 on top of my fraction. And there's only 2 sides to my coin. So that's why the bottom would be a 2. So let's look at some examples. And I've already got this one pre-worked out just so we can kind of look at it and count them. So let's say you have a fancier die, a 12-sided die. So that's going to have numbers 1 through 12 on it. The set of equally likely outcomes is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Each one of those sides would only occur once on the die. Find the probability of rolling, and we're going to write our answer in a fraction in lowest terms or an integer if it like reduces like some of these do. So a 10, well, the probability of a 10, notice we were using our notation, this is the event. There's only 1 10 out of 12 total sides. So that's where this fraction comes from. This says a number less than 8. Now, it did not say less than or equal to 8. So less than 8 is actually only 1 through 7. So a number less than 8, there are 7 of those out of 12 total sides. And 7 over 12 does not reduce. The next one says, what about if your number is even? So there's a 2, 4, 6, 8, 10, and 12. There are 6 even numbers in the list out of 12 total numbers. Notice this one I did need to reduce because 6 and 12 are both divisible by 6. The next one says a number less than 19. Now 19 is not even on our die, but all of our numbers are less than 19. So if this is what they're asking, every single number on this list is less than 19. So that's why we would say all 12 items out of all 12 items. and that reduces to 1. So if someone said this as a statement about a 12-sided die, you have a 100% chance of getting what they've said. You're going to roll a number less than 19, okay? That's what we call a certain event. It is absolutely going to happen. This one says a number greater than 13. Well, if you have a 12-sided die, you don't have any numbers bigger than 12. So there are 0 numbers in our list that are out of the 12 that are bigger than 13. So that would be 0, because 0 divided by 12 is 0. We want to actually reduce that. This is what we call an impossible event. Okay. So let's look at some examples. It was observed over the past year that it rained 95 of 365 days. What is the probability of any day being rainy last year? So this was past year. This is the data. We want the probability that it being rainy last year. So the probability of rain last year, we can take it directly from the information they provided. There were 95 rainy days, out of 365 total days. And we do want to simplify that fraction. So I don't have a fancy calculator that can do that for me, but I do see that they're both divisible by 5. So let's start there. So if I divide top and bottom by 5, that gives me on top a 19. We'll see if this is enough. 365 divided by 5 is 73. So the only question is 19 only has 2 factors, 1 and 19. So does 19 go into 73 evenly? It does not. So this would be our reduced form. And remember, I showed you how to do on your calculators the simplifying of fractions. So you could have done that without this step. Okay, let's look at another one. There are 5 cups lined up, and under one of the cups is a marble. If Anne randomly selects the cup, what is the probability she selects the cup with a marble? So we have 5 total cups. So we're going to look at probability of getting a marble. There are 5 total cups, right? And there's only 1 cup with a marble. So she has a 1 out of 5 chance that she's going to select that cup with the marble. Okay. This one, a lot of times students are not as familiar with decks of cards, and unfortunately, sometimes that's a big thing in probability. So let's just read through this. There are 52 cards in a standard deck of cards with 4 suits. So when they say the suits, they're talking about the little shape that's in front of the cards. So we have the hearts. So like if they had 3 hearts, you'd see 3 hearts on your card. We have the diamonds. So that's that symbol. I'm actually going to color these into their color. So hearts are a red card on a deck of cards. And diamonds are also a red card. There's also the spades, and I'm not good at drawing the spade symbol. Kind of looks like a circular thing with a pointed top. That's the best I can do on that. And we have the clubs. And the clubs look like a clover, kind of. Yeah, not known for my drawing skills. Go ahead and put that. And these 2 sets of cards are the black cards in a deck. Okay. So half of the cards in a deck are red and half are black. And that means 1/4 of the cards are hearts and 1/4 are diamonds, because it's an equal set of diamonds and hearts. There's an equal number of spades and clubs, so 1/4 each is in this group. Each suit has 13 cards. So that's what they mean. So 52 divided by 4 is 13. So each of these has 13 specific cards. And those cards are an ace, a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, a 10. Then we have the face cards. That's what they call the ones that have people on them. The jack, the queen, and the king. Okay. So now that we have a little bit of the framework there, let's do the probability. What's the probability of choosing a 7 out of a standard deck of cards? Well, there's a 7 of hearts, a 7 of diamonds, a 7 of spades, and a 7 of clubs. So there are 4 7s in the deck, and all of the cards in the deck add up to 52. So we would reduce that. You can divide both of those by 4. That is a 1 out of, I believe, 13. Let's triple check that. Yeah, 13 chance that if I just randomly pick 1 card from a deck, I will have a 7 in my hand. Okay. All right, for 6B2, we're going to look at the probability of not an event. What does it mean to do the opposite of event, essentially? So not events are finding the probability of not being something. It is called the complement. That's its math term of A, and we denote it as usually an A with a little apostrophe, but most of the time it actually looks like this when it's not use a type, like a text type, or some books use A of C, like for complement. We will use the A prime, okay? So this is the rule. If you are an event or you are not that event, so if I add the probability of an event happening plus the probability of the event not happening, that should equal 1. That's called the complement rule. If you think about it, we can show that in just a second with rolling a regular die. It's pretty easy to see it. So the sum of the probability of something occurring and something not occurring is 100%. So let's show you that. Find the probability of rolling a number that is not less than 5 on a standard 6-sided die. So not less than 5, okay? So the event A is rolling a number less than 5, because see, we've thrown the not in front of it. So those are the numbers 1, 2, 3, and 4. The event not rolling a number less than 5, that actually means rolling a number that is 5 or bigger, because we're doing the opposite. That would be 5 and 6. A die has total of 6 outcomes. If I want to know the desired outcomes, which was not less than 5, there were 2 of those, okay? There were 2 numbers that were not less than 5. So the probability of not less than 5 is 2 out of 6, which is 1/3. Now to show you, I could have found that using the irregular event, which is just rolling a number less than 5. We can use the complement rule. So that what they do with the complement rule is essentially, remember it said P of A plus P of not A equals 1. That means if you know either of these, you can find the other. So if I want probability of not A, I just do 1 minus the probability of A. So if I want not A, I just take A out of the equation, okay, from 100%. So notice 1 minus the probability of a number less than 5 would have been 1 minus 4 out of 6, right? Because there's 4 numbers that are less than 5. That would have given me, this is 6 over 6 if you make it a common denominator. So that would be 6 minus 4 is 2 out of 6, which equals 1/3, okay? So notice, there's a 2 out of 3 chance of getting a number less than 5. There's a 1/3 chance of getting not a number less than 5, okay? Because it's the opposite of what we have. Okay, so let's look at an example. It says if there are 5 blue marbles, 6 red, and 4 green in a bag, find the probability of drawing a marble that is not red. So it's really easy in this one. There's 2 ways we could do this. So not red, we could just count the blue and the green. We could just say, what do we have? Okay, well, we have 5 blue and 4 green. So that's 9 blue and green. So the probability of not red, just counting directly, would be 9 blue and green out of, we need to know our total marbles because we need that for the denominator. That would be 11 plus 4, there's 15 marbles. So 9 out of 15, which reduces to, let's see, divide those both by 3, that'd be 3/5. Okay, so that's the correct answer. And I got that by just saying, okay, if I can't use red, I'm using blue and green. Another way of doing the not red would have been to do the complement rule, would have been to do probability of not red is 1 minus the probability that I am red. So 1 minus, I had 6 red out of 15. I would go ahead and reduce that fraction before trying to subtract. Divide those both by 3, that's 2/5. Get a common denominator. 1 can be any number over itself, so that's the easiest number to make a common denominator with something else. So 5 minus 2 is 3/5. Okay, so either way, we got it. Now, sometimes we do have to use this complement rule where we subtract 1 minus what it is, the probability of that, because it may be too hard to actually count up all of the other items. So sometimes this is a necessity. This is using the complement rule. It makes things easier if we can't actually physically go through and count all the other individual items. And then I think this is our last 2 pages for day 2, probabilities with or overlap. So we're going to go over, like I said, a lot of these are just introductions to the topics. We're going to spend more time in class on doing multiple examples. But if you have the word or, so I want the probability of A, which is event, something, or a different event happening, so A or B. If the events are mutually exclusive, which means they have no overlap, which means everything in event A is completely separate from everything in event B, then the way you do the OR is you just add the two probabilities together. Now, we'll have to talk about later what happens if there is overlap between those two sets. So this is what we consider the easy way. So many problems can be done the easy way, number of desired events divided by number of total possible outcomes without using the formula. If you can count your desired outcomes, which means don't count your elements twice if there was overlap, and the total possible outcomes, you can do it the simple way. So let's just look at an example where we have mutually exclusive events. Mutually exclusive just means no overlap between event A and event B. A group of baseball fans was asked to name their favorite team. The top three answers were 41 choosing the Dodgers, 52 choosing the Yankees, and 17 choosing the Royals. So if you're listing a top favorite team, there should not be overlap. A fan has a singular top favorite team. Okay, so all of these fans in this group are different than all of the fans in the other groups. What is the probability that a fan prefers Dodgers or Royals? So the denominator is all the possible fans that they interviewed. So that was 41 people plus 52 people plus 17. So that's 110 fans total. The probability of a fan preferring the Dodgers was 41 out of 110. The probability of a fan preferring the Royals was 17 out of 110. So preferring Dodgers or Royals, since those two groups do not overlap, you're either a Dodgers fan or a Royals fan as your favorite team. You're not both at the same time. So this would be 41 out of 110 plus 17 out of 110. And when I added that, when we add fractions with the like denominator, remember you only add the tops. You are welcome to use your calculator on these fraction additions. Remember you have that accessible to you. But that is 58 out of 110, which reduces down to 29 out of 55. Okay. So let's look at an example of doing this. So again, we're sticking with the pre-video with the groups that don't overlap. We'll talk about what happens if they overlap in class. So a picnic basket is filled with sandwiches for students in the band. There are 52 turkey, 70 ham, 17 cheese only. What is the probability the band member randomly selects a turkey or a cheese? So they can only select one sandwich. And if you have turkey, you're not a cheese sandwich. And if you have cheese only, you're not a turkey sandwich. So no overlap between the sandwiches. So first of all, we need our total sandwiches because we'll need that for our denominator. So that's 52 plus 70 plus 17. So 52 plus 70 plus 17. That is 139 sandwiches that they brought. So probability of turkey or cheese is the probability of turkey plus the probability of cheese, because we already said there's no overlap. You're either this type of sandwich or this one. You're not both at the same time. So there were 52 turkey sandwiches out of the 139, plus there were 17 cheese-only sandwiches out of the 139. We add our numerators, so 52 plus 17 is 69 out of 139. And I don't have my fancy calculator down here with me, but let's just triple check. I think 69 is divisible by 3. Yes, it is. So I'm questioning if 139 is as well. No. 69 divisible by 23, well, because that was 3 times that. So let's check if 139 is divisible by 23. I don't think this one reduces. Type it in on your calculator and double check. I will also let you know in class if I find that it reduces. But that is what I got for this one. Okay. All right. Actually, let me check 13 real quick. I'm not 100% sure if it doesn't reduce. 16 divided by 13. No, it doesn't go evenly. Okay. So 6B4, probability using and. So notice the connection between the words is and this time instead of or. We are going to spend a lot more time in class defining those two features and what the difference is, but let's just look at the generic kind of setup. This section also will cover conditional probabilities and contingency tables, which I did not put all of that in our pre-video, but that's just what the last section covers. So probability using and, which is written as P of A and B, to have an outcome in A and B, that means that whatever the outcome or event that we're looking for, you must be in both B and A at the same time. So like, say we were doing a deck of cards, if I wanted the probability of drawing a king and a heart, that means I have to be a king card and I have to be a heart card at the same time. There's only one of those in the deck, but so that's what the and statement means. I have to have both conditions at the same time. So let's look at an easy example with dice. So A's event is rolling an even number. B is rolling a number less than 3. And is the intersection of the criteria. To be part of this subset, you must meet all the criteria. So if we think about our even numbers, we have on a die, a regular die, that's a 2, 4, and a 6. A number less than 3, which means not including 3, because it didn't say equal to, is 1 and 2. The only element that's in both A and B, even number and less than 3, those two events, is the 2. Now these are numbers, but that is not our numerator. This is one item out of 6 total items. Okay, so you don't put the number 2 as the top of your probability, because 2 is the number of dots on the die. It's not the actual how many 2s are on a die. Okay, so be very careful about that. So find the probability of rolling an even number and a number less than 3. So probability of even and less than 3, we saw that there was only one side of a die that fits that. It's the face 2, okay, out of 6 total sides on a die. All right, let's look at this one. Roll a standard 6-sided die, find the probability of rolling an even, and that connection word is important, a number greater than or equal to 2. Okay, so even, I always write out what my numbers are, is 2, 4, and 6. B is greater than or equal to 2. So that includes 2. So 2, 3, 4, 5, and 6. Notice this time it's a little easier to see what we're talking about. There are 2 elements, actually 3 elements. 3 elements that are in both groups. I didn't see the 6 connection. So notice that this is in both, this is in both, and this is in both. So the probability of being even and greater than or equal to 2 is 3 elements out of 6 total elements on a die. So that would be 1/2 if we reduced it. Okay. And let's do our final problem. Find the probability of rolling an odd number and a number less than 5. So we're going to make our list again. A is odd, so that would be 1, 3, and 5. B is less than 5. So notice don't use 5 because it did not say equal to. So 1, 2, 3, and 4. I like to highlight these. So it looks like we have a 1 in common and a 3 in common. That means there are 2 elements in common. So the probability of being odd and less than 5 on a 6-sided die is 2 of the outcomes were both, the 1 and the 3, and 6 outcomes total for the sides of the die. So that one reduces to 1/3. So what we're saying there is if you roll the die, the probability that the number that pops up is odd and less than 5, you have a 1 out of 3 chance that that will happen. Okay. I hope this was helpful. We'll do a lot more of these together in class. All right. Have a good day.